Okay, good morning everyone. Welcome to another monthly QuakeCoRE seminar. I'm Brendan Bradley and I'm pleased to introduce Tim Sullivan here today, who's going to be our speaker for August. Tim has a bachelor's degree from the University of Canterbury. He then spent about 7 years in the consulting sector, both in New Zealand and then subsequently in London. Then he went to the University of Pavia to do his PhD and then also became a faculty member there. And 2 years ago, he returned back to New Zealand to the University of Canterbury, and now he's both a PI and also on the leadership team for QuakeCoRE. So thanks again, Tim, for giving the seminar, and we look forward to hearing what you're talking about.
Great, thanks, Brendan. So the title of my presentation today is Cost-Effective Consideration of Non-Structural Elements. And it's we're not going to be talking about all the cost-effective considerations you could make for non-structural elements. Just a few lessons we've learned by looking at a building that was subject to the Canterbury earthquake sequence. I'd like to acknowledge my co-authors in this work. So a lot of the material I'm presenting comes from work by Francisca Sarafin, who did his master's on looking at this building. Co-supervised by Greg McRae, and we had a project that involved collaboration with colleagues in Japan, Associate Professor Masahiro Kurata and his student Tadahisa Takeda, so I'd like to acknowledge all of them. For people who are interested, some of this material has just been published at the European Conference for Earthquake Engineering, and we've got a journal paper in preparation. So what are the background and objectives to this work? Well, it's been recognised actually for a few decades by different people, but increasingly so now in recent years, that the seismic performance of non-structural elements is relatively poor. They tend to be not engineered, and who's responsible for their seismic performance is sometimes put up for question. And they're very vulnerable. So we see the likes of the sort of damage you see here, maybe glazing damage, maybe a mechanical services damage, pipes can get broken, contents damage. And there are a range of different elements. We'll be looking at different ones today that were particularly critical for this building. So to reduce losses in future earthquakes, we should be considering these non-structural elements more carefully in our seismic design, retrofit and or rehabilitation of a building. And by rehabilitation, I'll be talking about what do we do when we've got damage to a building? Do we just repair that? Or what sort of general strategy could we have to address the seismic performance? So we're going to be trying to learn about what we could do to non-structural elements by looking at this case study building in Christchurch. So what is the case study building? Well, here's an image of it. It's a 22-storey building in downtown Christchurch, and the structural system has steel eccentrically braced frame system. We obtained information of this building by going to the local council. Here you can purchase drawing files and documents, and they included actually information on the seismic reports and damage. Not complete information, but quite a bit. So what you can see, a few interesting points to note is precast concrete cladding with perforated windows, if you like, up the height. Quite extensive over these upper levels. Another interesting detail, if you look at the plan, it's a mixed-use building. So this is showing a residential type layout, which is over the most of the building, say 2/3, and a lot of partition walls. Okay, and you've got eccentrically braced frames in around here, and you'll see the structural model we developed in a minute. Another thing you can see is a foundation plan and pile foundations, and we'll talk a little bit about that too. So what we did was we tried to this building was not instrumented, so we don't know exactly what it went through. And the master student, Franciscus, he developed a model for this building in Ruamoko 3D, which is a program where we used lump plasticity elements. And it's hard to get a good view of the model, but this is showing a bit of the model. You've got a series of EBF systems, both centrally located links, what they call centrally located, and D-type links, where the link is at the end of the brace. We've also modelled here the cladding, and we'll talk about why we did that in a minute. There were a few MRF frames just in the upper 2 stories, but generally the lateral load resisting system is the steel eccentrically braced frame. We had to make assumptions about a few things. For example, damping, we put 3% damping. We estimated foundation axial stiffness. So we didn't, if you look at the foundation plan again, we're recalling it's a pile foundation. In EBF systems, the axial stiffness can be quite significant in providing a rigid body type rotation. So we made an estimate based on geotechnical information that we had in the geotech report. But we also did sensitivity analyses to our modelling assumptions. We tried varying, for example, we ran 2% and 5% damping and reran and looked at the results and tried to gauge whether our conclusions would have changed, and they wouldn't, in the sense that what we're going to talk about today, our conclusions wouldn't change. Some other important assumptions perhaps is that the stairs have no effect on Storey stiffness, and the floors are modelled as rigid diaphragms, and precast panels were modelled. So why did we model our precast panels? Well, I should qualify that all of this modelling analysis was all based on the drawings we had. So we didn't have access to the building, we didn't go and verify. But if you look at this, this is a drawing detail showing the precast cladding panels. And you have to recognise that the cladding panels are going sort of, what you can see here is the bottom of a panel, and you can see the bottom has a plate cast into the concrete panel, which is then put onto the floor and cast in and grouted in here. So that's a definite rigid support at that point. So what's happening at the top of the panel? At the top of the panel, if you imagine here's the top of the panel from the floor below, comes up and there's a gap, and there's a steel plate with a single M20 anchor going into the top of the panel, or you'd have a couple at the tops of each panel, and then an angle coming off of that, which is attached to the bottom of this steel beam, which is going around. So it's clearly not it's not a completely rigid support, but if you do some analyses, and we did a little analysis of the connection detail here. If you can imagine a single bolt clamped onto the panel, if you try and push that angle laterally back and forth, it'll twist and bend, and you'll get some let's say, what was it called, leverage? No, prying effects, where you will get some moment resistance and some lateral resistance from this connection. So we estimated what that lateral stiffness was, and then the model was developed with these equivalent diagonal struts to represent the stiffness of the cladding panel, and a little beam element, which is representing the stiffness and also the strength. This was modelled with a nonlinear element of this angle connection. So we're expecting some restraint from these cladding panels, and we'll look at what the influence of that. So what ground motions has the building been subject to? Here you can see the main shocks, let's say, from in the Canterbury earthquake sequence. We had the main magnitude 7.1 September 2010 event, the February 2011, June 2011, and December 2011. These were all fairly significant events, considering that our building's in the CBD. Okay, and if we look more closely, we had actually 4 recording stations that could have been relevant to our building. You can see them here, one at the top, and then these 3 that are circled in red. The 3 that are circled in red had similar soil profiles to our case study building. So we had a soil profile for the site, and we looked at the 3 of those, and they were fairly similar, whereas the northern one was quite different, so we didn't use that one. So what we did is we said, well, we're not sure what this building was subject to, but we could run these ground motions and look at the behaviour under those and try and anticipate what the likely behaviour was. So here you can see the north-south response spectra for those 3 sites, averaged across the 3 sites. And you can compare that with the New Zealand standard 500-year return period intensity level, and you can see that both the February 2011 and the September 2010 event were quite significant. I should point out that this building has a long period, or long periods. Given that it's 22 stories high, we had periods of vibration of around 3.8 seconds estimated. Obviously, those depended on how we estimated our foundation stiffness and so on, but with our different modelling assumptions, it was around about 3.8 seconds. When we ran the time history analysis, so we took those ground motions at each site, we ran them sequentially. So you can see for a given site here, for a given station, we had the September 2011, September 2010, February 2011, June, December, and we put in a 100-second trace between those so that when we run these analyses and our building gets damaged, we don't forget that when we go and look at what was the likely impact of the February event. Of course, if they'd done repairs between the two events, you could arguably say we should have modified our model. In fact, we'll talk about, well, I'll tell you now that the building was, we understand that the EBF system wasn't repaired between these two events, so they were planning to repair it, but repairs hadn't been undertaken. So we think that's not too bad. I should also point out, which is written here, that in fact this approach, while we think it to be most rigorous, actually didn't make that big a difference. Okay, so in terms of at least loss estimates, which we'll be talking about, didn't really change it too much whether we ran them individually or sequentially. Here are some of the results of the time history analysis. First, I'll show you Storey drifts, and then I'll show you floor acceleration demands, peak floor acceleration demands. So here we're looking at peak Storey drifts. And these are, again, the average for the three different sites. And you can see some fairly significant Storey drifts. So in the north-south direction here, the September 2010 event seemed to cause the biggest drifts of close to 2%. The February 2011 caused over 1% and again close to 2%, so 1.5%. And an interesting distribution of drift demands up the height as well. And when we looked at damage, those drift distributions tended to correspond pretty well with where they reported damage in the links of the EBFs. In terms of floor accelerations, here are our peak floor accelerations of about 0.4 G. So some of you will be experienced with looking at peak floor accelerations, peak Storey drifts, know what's big, what's not, what's significant, what's not. But just to put this into context, here are some fragility functions that we used. So we use fragility functions to take those drift and floor accelerations and try and work out what's the likely damage. And the two, I'll point out two here, the exterior cladding panels. There are fragility functions developed by Beard which suggest that cladding panels start to get damaged at about 0.2% drift. Okay, and if you look back at a minute, we had Storey drifts, 0.2% drift is down about here. So you're expecting damage to cladding panels in just about all those four events. Similar for drywall partitions, Storey drifts of about, let's say, 0.3% drift will cause damage and repair requirements. So again, significant damage you'd expect in all four events. Should point out also though that the cladding panel detailing would be can vary greatly from one building to another. Perhaps not exactly applicable to this building. We didn't have much else to go on, but so we used this, but that's possibly a point of uncertainty. Well, a big point of uncertainty. In terms of acceleration sensitive elements, these are the acceleration sensitive fragility functions. So I should clarify for those who are not familiar, some types of elements like ceilings and pipelines and so on are more sensitive to the shaking itself, the accelerations that you feel, whereas others it's the drift we're imposing on the element, how much deformation. So that's why I'm classifying the two. So if you look here, the most sensitive, acceleration sensitive element was the sprinklers, and they're expected to start getting damaged at about 0.95 G. So we can conclude from this sort of quick, even if we're not sure about the fragility of these different elements, what is clear is that we're not expecting a lot of acceleration-induced damage to our non-structural elements, remembering that we had floor accelerations of up to about 0.4 G. Okay. So what we did is we used those fragility functions together with cost functions, and there's some cost information on the right side of those tables I was showing you with the references here. We took more attention, if you like, to the drift sensitive elements in terms of costs and so on. We consulted a bit in terms of the EBFs. We talked with local engineers about what was the cost of repairing EBFs typically. And using that information, so we're able to take the peak floor accelerations, peak story drifts, work out damage states or likely damage states, and from that information work out likely costs. And this is showing the results of that study, where you can see damage to partitions in all 4 events. And recognize that those events are occurring at a fairly spaced out time. And some of those partitions are required for fire safety. So you have to repair those partitions before you can safely use the building again. So we have to repair the partitions here, we have to repair the partitions there, repair them again. And obviously that's quite a lot of inconvenience, so downtime, and also cost. You also had the panel connections being predicted to be damaged, as we suggested. The panels are set in themselves as well. We distinguish between the two there. EBFs would have been damaged in the September event, but we haven't shown their costs here, as I said before, because we said, well, we haven't repaired them in time. So we just put all their repair costs in there. They weren't expected to be damaged in those subsequent events there. So what are the observations I want to make about these results in this study? And there's 3. So the impact of non-structural elements on repair costs of damaged structural elements. So this is one of the links in the steel EBF frame. These are short steel elements, part of a longer beam element, where the braces come up and they're designed to undergo inelastic deformation. This particular link has undergone too much inelastic deformation and it's fractured, but ideally you would see just maybe the paint cracking and you could repair that. You could repair this anyway, you have to cut it out and put in a new section. But okay, so we had damage to the links all the way up the height, and you would say for this sort of earthquake event, which was a rare event, this is expected. Now, down below, we've got 3 different damage states for these links, and we've got indicative costs here. We put everything in US dollars. Perhaps, yeah, well, that makes it easier for our international people to understand how much that means. But the important point I want to make here is look, here's a link at a given floor. Now, you haven't got as good a view of the link, and why is that? Because we've got all sorts of non-structural elements and services all around that link. So to repair that link, where they have to get access and actually remove and replace or do any sort of, so they have to replace the concrete slab, they have to reroute the non-structural elements and look at the cost of that. So our first damage state, about $20,000 to repair an EBF link for damage state 1, of which $16,000 is the cost associated with removing or moving our non-structural elements. And of course that cost is expected in some of those higher damage states as well. So what is the lesson to be learned from that? Well, from my point of view, the important lesson there is that we should be considering the location of non-structural elements in our concept design stage for the structure. Okay, so here are just some arbitrary sort of, okay, if we were thinking about architectural and mechanical services drawings for a building, maybe this is a new design building, the question we'd have to be asking ourselves, if we know where the services are likely going to go, where's the best place for us to be putting our structure? what sort of structure can we be putting in that will mean that we have least disruption from the non-structural elements and vice versa. Second important observation from this study was the role of the precast cladding on the seismic performance of the building. So as we talked about before, this cladding was detailed in a manner that seemed a bit unusual. Why do I say that? Because normally what you'll attempt to do is have the cladding panels restrained laterally at one end, either the top or the bottom, and free to undergo lateral deformations at the other end. So that the cladding panels are just sort of sitting or hanging from the slabs and going for the ride. Okay? They don't restrain the lateral deformations of the building. If they restrain them, they get damaged, and that's what we saw. Okay, so we asked ourselves the question, so how would the seismic performance of the building been affected if the cladding had provided no restraint? Clearly the cladding would have been damaged less. Is this better? So what we did was we reran the time history analyses with and without the cladding panels. Okay, so we can just take those cladding panels out, rerun the time history analyses, and we get a new set of drifts and a new set of floor accelerations. Where are my floor accelerations? Here. So floor accelerations didn't really change too much. Storey drifts, though, changed quite a bit. Okay, you can see in the dashed line the drifts associated with no cladding restraint, and in the solid red lines the drifts we've got median and plus and minus a standard deviation, I guess, for the cladding restraint. No cladding restraint. Oh, sorry, I'm sure you understand by now. So significant increase in drifts, not big significant increase in floor accelerations. Would it have been better for our losses and performance? Well, clearly we have now we're assuming no damage, no loss to the cladding. But actually the overall building repair costs increase. Why was that? Why did our building repair costs increase when we've just avoided damaging our precast cladding panels? Because we had so many partition walls which were getting damaged, and now they've undergone much more drift, that we predict we would have had more damage and more cost to repair those additional non-structural elements than we would have with the precast cladding. So what's the lesson here? It's not to say, okay, we should be going and using this detailing for precast cladding. It's to say sometimes the impact of our detailing decisions and also say things like cladding panels, the impact is hard to assess. We have to think about it fairly carefully. The third observation I want to make is about the role of aftershocks on the seismic performance of the building. Perhaps this is obvious, but if we look at our most damaging earthquake, in this case it was an aftershock. I guess some people would debate whether this is an aftershock or not, but what's clearly important here is we've got damaging events occurring in multiple times. Okay, so are we considering this in our loss assessment when we're doing loss assessment of buildings? And what about our repair strategies? We needed to repair, we expect they needed to repair these partition walls multiple times. And as I said before, the fire rating could be important, acoustic, generally just visual is also not nice for people to have to live with. So what we asked ourselves though is we said, is this just specific to Christchurch? Okay. Obviously Christchurch was very unlucky. Right, we were in the wrong place at the wrong time. So what we did, and I'm sure you could do a more rigorous and comprehensive study, but as part of this master's research, we looked at 3 different large earthquake events, Darfield, Kumamoto, QuakeCoRE, and we searched for pairs of stations which were equal distance from the main event. Okay, why was that? So you can see up here 9B, 9A, 8A, 8B, and they're about the same sort of distance. So we had 2 stations there. We said if this is the main event, clearly Christchurch was a bit unlucky because it was located where all the main aftershocks occurred. And you could have said, well, if it were over towards the Alps, it would have been much less damaging. So we're saying, well, let's say it's equal chance of being either northeast or southwest of the location. So we searched for pairs, and then we reran our time history analyses for those different pairs, recalculated losses, given equal probability of being in either location. And the results are shown here. Some of those were obviously, because we're quite far from the main event, smaller intensity, and some of them bigger intensity. And for some cases, you see a very big increase in expected losses due to the aftershocks. So this is showing total losses, thinking about just calculating them from the main shock only, or the main shocks and the aftershocks. And a general sort of a trend is, say, of about 10% increase overall. So we believe the issue of aftershocks will tend to increase losses. Wasn't just specific to Christchurch. Christchurch was clearly an extreme case, an unlucky case, but we do think that it increases losses. So it would clearly, another lesson here is, clearly have been beneficial to repair our non-structural elements with improved detailing. If on day one they'd said, let's go in and repair those partitions, not the same way we've been doing them all the time, but with a detailing that's going to give us a bit more drift capacity, maybe a very marginal increase in cost, because you're going to have to repair them anyway, we could maybe have avoided the additional damage and losses. So the conclusions of this work were that through examination of this 22-storey building, we have the following findings. The first, and so I'm just recapping what we've talked about already, decommissioning and rerouting of non-structural elements can affect losses significantly. This should inform our concept design decisions. A building will be more repairable if non-structural elements are not close to plastic hinge zones. That's a bit of a challenge. How do you do that? The effect of non-structural precast cladding on losses may be hard to estimate without modelling and analysis. And maybe that's a more general, you could make that a bit more general and say, well, it could be certain types of non-structural elements. It's a bit hard to anticipate. We have to step back and think carefully before we decide on their impact. And aftershocks can increase losses significantly and should be accounted for in loss assessment studies. I'd like to acknowledge the funding that supported this research. So we had funding through this International Collaborative Research Program with Japan, and the QuakeCoRE flagship, and the Indonesian government that funded Franciscus's master's thesis. Thank you.
Thank you so much, Tim, for the great talk. Lots of interesting information there. A chance for either people in the room here at the University of Canterbury or people elsewhere on the video call. If you're coming from the video call, interested to ask a question, please just say who you are and where you're from, and I'm sure Tim will be interested to take a few questions.
So you're talking about the non-structural sort of service elements that were getting in the way of repairing non-structural components. Is that because they had to completely remove them and then put them all back in as new kind of components? Or was that just a sort of labour cost in terms of they already had sort of fittings that they could remove sections of the pipes and so on?
No, so they needed to remove them to be able to safely prepare a support for the concrete slab that needed to be poured. So you had to actually remove them, and they weren't damaged, but they had to be removed as part of the repair works for the ABS.
But so it's essentially a labour cost rather than a material cost.
Oh yeah, no, usually for these services it's often labour. I mean, maybe say for some sort of IT cable or something, or maybe there's a bit of material, but a piece of pipe doesn't cost too much, but it's getting people in.
I mean, I guess the extension of that is the flip side of that is maybe the existing design is okay, but we need to be thinking about how in earthquake regions we can make those sorts of elements easier to just get out instead of trying to change the...
Sure, yeah, a good point. And sometimes even trying to inspect your structure is costly, because you need to be able to get in there and look and see whether your link was damaged, and maybe there's a ceiling in the way, or that would be ideal. But sometimes for floors, they have to pull back carpets and so on, and you can cause damage. Maybe you have to rip off linings. Maybe if it's tiles, how do you know whether the concrete floor is damaged? Okay.
Well, I guess I have a broader question about how much attention is given to non-structural components generally in design practice here in New Zealand. I mean, specifically, how much attention was given to design specifications for non-structural elements before the earthquakes? Has that changed at all after the earthquakes? And how does that compare to, say, other parts of the world? Say, for instance, what is your experience in Europe, and how is that different or similar to what's done here?
Okay, thanks for the question. So my impression is that following the earthquake, engineers are giving a lot more attention to non-structural elements. However, they're not necessarily designing them, and still, that's not part of their scope. Yeah, I say that, and I'm aware of different engineers coming out with new partition detailing that they believe will lead to less damage, and that's a non-structural element. There's still a lack of responsibility in the industry in terms of, well, that's my perception, in terms of who would be responsible after an earthquake for that damage, and who's writing a producer statement, if at all, about seismic performance, and would that mean anything if they wrote it? So there's coordination issues. There's issues that the industry are telling us that one of the major issues to seismic performance of non-structural elements is that things aren't being braced correctly, or they're not being done according to the existing code, the current code requirements. And yet, how do they ensure that? Who's checking it? Who's coordinating it? Because if they go and put in a sprinkler pipe braced in a certain position, they put the brace that's going to now make it difficult to brace, say, another type of service, then it creates all sorts of problems. Going into international practice, generally non-structural elements are not well considered in the design process. We have drift limits and we have floor accelerations, and as part of the design, the structural engineer will estimate what the building needs to go through and perhaps give that information to the architect, who should include it in their specifications, so for glazing and so on. And then the glazer tries to ensure that they're going to sustain that certain drift. The only exception I'm aware of is in the States for hospitals, where they have a specific requirement for someone to go off and check that all the non-structural elements are detailed according to seismic provisions, and they have to sign it off. So there's someone who's taking responsibility for checking, basically.
I'm Uma here, Tim, from GNS. It's a very interesting topic, and research has been done. Thanks for that. My question here is about the acceleration, floor acceleration that you have observed from your analysis up the floors. When you compare it with the design standard like 1170 Part 8 or even 4219, they have a different layout. What is your comment on that? I mean, is it increasing up the floor height, or how do you want to comment on that difference between the recommended layout of the floor acceleration and your observed floor acceleration?
Yeah, okay, we could do a whole talk on that too. Good point. I guess the key to note is that peak floor accelerations in a tall building will tend to be fairly low, as a long period. They have low base shear resistance as a fraction of the building weight, and they tend to therefore develop relatively limited peak floor accelerations. But we didn't plot what I would call peak floor response spectra, and you could have expected bigger floor acceleration demands at the characteristic periods of the building, maybe bigger spectral displacement demand. And maybe that's a side point. So if we just focus on the peak floor accelerations, and you would have applied the New Zealand standard or any other international standard predict those floor acceleration demands, you would have probably been predicting much bigger floor acceleration demands in this case. My feeling is that that's arguably because those are really being aimed at lower, smaller buildings. But I would say that my research and others that have published a lot on this topic have shown that there are real limitations with our code approaches. So we can't hold a lot of confidence, and they can be conservative, but they can equally be very non-conservative in predicting floor acceleration demands.
Because the design engineers right now, even if they are able to adopt the recommendations, are they doing it safe or not? That's another thing.
Yeah, no, that's a good point. So in this particular building, perhaps it wasn't such an issue if the elements were braced. We've got pretty good performance. But if you happen to have non-structural elements that have a period of vibration, say a sprinkler system, which happens to have a period of vibration that corresponds to, say, the second mode period of vibration in, say, a 4-story building, you could get floor acceleration demands that are maybe 10 times bigger than the code prediction. So even if they've gone and braced things correctly, you'd be worried that you'd anyway get some damage. No, that's a subject really for more research.
Yeah. Will there be any recommendations on that from this research at all on the test?
Not on this, from this research. I have a master's student currently looking at floor response spectrum. We're hoping to come up with something. And I've just had a PhD student finish his PhD on the topic, just finished a year and a half ago now. So
Thank you, Tim.
Okay.
Tim is coming back to the comment that you made already, comparing the structural analysis response without consideration of the partition stiffness and strength, and then with consideration of that.
Yeah.
Do you think that as consulting practice moves towards a lot of the use of building information modelling, where it should become much more straightforward to include non-structural elements in structural analysis, that people should routinely be considering it in their dynamic models? Or do you think this building was maybe a particular case where those facades actually do contribute, but in many cases the connections are such that they maybe don't contribute?
I'd support the general approach to try and detail your non-structural elements to not provide stiffness to the building. So this was a little bit of an exception. However, I also support the idea of a different way of doing our elastic damping modelling. And currently a lot of our damping assumptions are, well, part of our damping we say is coming from non-structural elements. And there are hysteretic models, there are ways of modelling. You mentioned actually partitions. We can model partitions. We didn't in this case. You can model cladding, you can model glazing. So if we want to do a better job of sort of getting away from this uncertainty that we're introducing through this percentage of damping, how about we go and model our non-structural elements? And people have done some things on that too. Regan.
The loss estimates and the damage estimates that you compute using your numerical model, I just want to check if you by any chance compared them to the actual damage incurred in the building and the actual losses incurred in the building post the earthquakes.
So we don't have information on the losses. That's not it. We couldn't get access to that. We don't have it. But we do, from the council reports, there was reports of which elements got damaged and generally what floors, over which floors. And there was good correlation both with the fact that they had cladding damage, they had a lot of partition damage, and they had EBF damage over the levels that we were predicting. So we got pretty confident that.
Anything in the acceleration sensitive components?
That I recall, no, there was no reported. But maybe I'm wrong there. Yeah. But not significant.
Okay, sounds like we're winding down with questions. So thanks again, Tim, for the great presentation. And just a reminder to everyone, these seminars occur monthly and this seminar has been recorded, so it is possible to view afterwards as well. So you can let anyone who missed this presentation know that they can access it online. So thanks once again, and we'll see many of you next month.